Good afternoon, all. We welcome you all to the fourth day of AICT Training and Learning sponsored online FTP on emerging trends in electric vehicle ecosystem, power electronics, AI, and sustainable mobility. Today we have with us engineer Alex J. Paul and engineer R. Akhil Raj on the topics in electric vehicle, emerging topics in electric vehicle. So for the official welcoming, I invite Amrita Roshan, IEEE student volunteer, for the official welcome.
Thank you, ma'am. So, good evening, everyone. Welcome back to day 4 of our ATL sponsored online faculty development program on emerging trends in electrical vehicle ecosystems. We now move on to session 7 on the topic EV communication protocols and cybersecurity. It's my privilege to introduce our eminent speaker for this session, Engineer Alex J. Paul, currently working as a SoC Logic Design Engineer at Intel Technologies Private Limited, Bengaluru. Engineer Alex J. Paul is a highly accomplished RTL and VLSI design professional with over 14 years of industry experience in semiconductor technologies, FPGA design, SoC development, and hardware verification. His career spans across leading organizations, including Intel, Tech Mahindra Sirium Systems, Wipro, Dexel Electronics, Satava eTech, and NXT Semiconductor Technologies, where he has contributed to cutting-edge projects in 5G, pre-5G base stations, image processing, industrial automation, and advanced FPGA implementations. At Intel, he has been instrumental in IP logic design and SoC integration, working on high-speed communication systems such as Ethernet IPs, DDR-PHY test chips, and advanced control ICs. His contributions have been recognized with Customer Excellence Awards for his problem-solving, ownership, and collaborative spirit. Academically, he holds an MTech in VLSI design from Hindustan University and is currently pursuing a PhD in artificial intelligence from the National Institute of Technology, Tiruchirappalli, focusing on deep learning applications. Beyond his technical achievements, engineer Alex J. Paul has also presented research papers in international conferences and actively works on bridging academic research and industry innovation. So, we are truly honored to welcome Engineer Alex J. Paul today, and we look forward to gaining valuable insights from his rich expertise and inspiring journey. So, we warmly welcome you to begin the session. Over to you.
Good evening, all. Can I start?
Yeah, sir. Yes, you can start.
Yeah. Okay. Good evening, all. Thanks for the warm welcome. First of all, I would like to thank the Christ College of Engineering for giving me an opportunity to share my knowledge on the communication protocols. So I'd like to share my screen. Okay. Hope you can see my screen, right?
Yes, sir. Yes, sir.
me a minute. Yeah. Can you see my screen?
Yes, sir, but it's okay. It's more visible if it is in the screenshot.
Okay.
I mean the slide show.
Yeah. I stop share and share again. Is it okay now? Hello?
Sir, it is also in the not in the
Full screen? Not in the full screen? Hello?
No, sir.
Okay. Mm,
Sir, can you please start the slideshow?
Sir, please press F5 on your laptop. F5.
function. Yeah. No, already I am in full screen only, but
Sir, while you are presenting, can you select the screen instead of window or
okay, sure. Can you see my screen now? Hello? Hello?
yes, we can see the screen, but you had yeah. Now it's okay. Now it's perfect.
Okay, fine. Okay. Okay, so today's topic is EV communication protocols and cybersecurity. So with this, I would like to start the presentation. Before that, I would like to thank the management of the Christ Engineering College, the Department of EEE, and the management and the staffs for giving me an opportunity to share my knowledge on this, mainly on the communication protocols. So what does a communication protocol means mainly? So a communication protocol is a set of rules and conventions that define how two or more devices exchange data over a communication medium. Usually in the electronics, in the field of electrical and electronics, there will be multiple peripherals will be talking each other, mainly to CPU, to another peripheral device like temperature sensor or 7-segment display, or there can be multiple memories talking to each other. There will be data transferring from one peripheral to other peripheral, or the CPU will be getting the data from a peripheral, or the peripheral will be sending a data to the CPU. So while transferring data among these peripherals, there should be a common medium and common standard has to be followed to transfer the data from one peripheral to the CPU or the vice versa. If the standard is not followed, if the data or if there is not, if a set of rule is not followed, then the data whichever is sending from one peripheral to the other peripheral will get mismatched, and the data cannot be whatever the data you are sending to the other receiving end will not be conveyed properly. To get a proper convey, if you want to properly convey a data or properly convert some message to one domain or one CPU or to another peripheral, there should be a common standard has to be followed among these two devices. So that is what we call it as a protocol. Mainly in the communication point of view, we call it as a communication protocol. So what does this communication protocol specifies mainly? It will have a format of data which has to be followed by both the ends, either the receiver or by the sender. It has a transmission rules, how the transmission has to happen, who sends first. So this kind of transmission rule has to be there. So the next one is what has to be there is it has to have a error handling mechanism, and then it has to have a flow control, and then it has to have a addressing and arbitration. What does this format of data means? So format of data means either it is sending the data in a bitwise or bytewise. So what is the message it is sending? So what is the length of the message? And whether it is sending in a frame based or it is in a bit based or it is in a byte based. So what is the structure of the data which is going to send by both the peripherals? And other one is the transmission rules. So if there is a two communication devices communicating each other, then one will act as a master and other will act as a slave. So in that case, who will act as a master? Who sends first? And when to send the data? And at what speed the data will be sent? So how the data will be synchronized between these two peripherals. So this is the transmission rule which has to be followed by two peripherals or the two devices. And then the error handling mechanism. Error handling mechanism is nothing but whatever rules or transmission rules or the format of data you followed, there can be chances of some errors in the transmission medium. So how to detect this error and how to correct this error? So depends on the criticality of the data you are sending. The correction mechanism will be included in the communication protocol. And then the flow control. So how many data you are sending? How to prevent the overflow of data? You can keep on sending the data, but the other end, if it doesn't receive the data properly, or if there is not a buffer length, if the buffer length is smaller in the other receiving end, then the data will overflow and there can be a chances of data loss. So how to avoid this flow control? How to avoid this? We need to have a flow control mechanism in the protocol. Then comes the addressing and the arbitration. So each peripheral will be identified with an address. So which address represents which peripheral? So if you have a master and if it is sending data to a multiple peripherals, then all the peripherals can assume that this data belongs to myself. So, but it may not be the true. In the real time, it may not be true. That particular data and particular information corresponds to a particular peripheral in the junk of peripherals. So in that case, so which data and which information belongs to which peripheral, that will be identified with the help of the addressing mechanism. And then the arbitration, how to take the data and how to fix the data, how to use the data. So this kind of standards and this kind of format will be followed in the communication protocol while transferring the data from one device to the other device. So that is how a communication protocol exists, and it has this following specifications has a communication protocol has to follow. So what are the types of communication protocol? In the electronics field, there are two kinds of communication protocol. One is on-chip communication protocol and other one is the external communication protocol. So what does this on-chip communication protocol represents? So on-chip communication protocol is nothing but in the modern world, everything is run by a VLSI chip or by a electronic chip that is equal that implements in the EV vehicles also. In the EV vehicles also that holds good. So in the communication is happening in all the EV vehicles, that is in the automotive also. That is the on-chip communication is the communication protocol which is used within a chip. In every chip, there will be multiple peripherals internal to the chip. So these chips will be communicating with the particular protocols like AMBER protocol. AMBER protocol is nothing but a protocol which is used in the ARM processor. ARM processor is nothing but a processor which is evolved from the RISC-V architecture. So with the RISC-V architecture, we will be using there is an ARM processor. In this ARM processor, mainly it uses the AMBER protocol. The AMBER protocol has multiple types of protocols, which is like AXI, APB, and AHP. Based on the need and based on the speed, we will be selecting these protocols. APB will be the slower protocol. AHP will be much faster than APB, and AXI is the high-speed protocol. So if you want to transfer a small data which is at low speed, we will be using APB. If you want to send the data at bit higher speed, then we will be using AHP. Then if you want to access some memory or something like that, then we will be using AXI. So these are the protocols which are used within a chip. So these protocols will not be useful if you want to transfer data from chip to chip. These protocols will not be useful. So what is the external communication protocol? External communication protocol, there are many external communication protocols. One is the I2C, which is of lower speed, and SPI, but bit higher than the I2C, and UART. Then we have Ethernet. Then we have CAN, controller area network. Then we have LIN, that is local interconnect network and FlexRay. And then we have MOST, which is multimedia oriented system transport. Then we have EVSC, which is electric vehicle supply equipment. Then we have vehicle to everything, V2X, and then we have telematics. In this CAN, LIN, MOST, EVSC, and vehicle to everything are specific to the automobile. Automobile communication protocols are mainly this: CAN, LIN, MOST, EVSC, and vehicle to everything. And also there is a automotive Ethernet. One protocol is there which is used in the automotive. Ethernet is used in the other applications also, and also in the automotive also we will be using the Ethernet, which is of automotive Ethernet protocol. So how does a system, actual EV system work, and how does a EV communication happens? So this diagram shows how a EV is used. So we have a EV system, EV car, which is charged by a charging station. This charging station will be using some protocol to charge this EV vehicle. That is the external protocol to the EV, to the vehicle. So this vehicle will be communicating with the external world through the some certain protocols to the charging station. Other than this EV vehicle will also communicate with the wireless network through the GPS, through some communication systems, through LiDAR, or through monitoring system. This kind of monitoring systems is also used some certain communication protocols that is used external to the EV vehicle. Along with this, EV vehicles also has some electronic control units internal to the system. So it is called as in-vehicle control unit protocols. This in-vehicle protocols also used in the EV vehicles to communicate within a vehicle. So let's go somewhat in depth in the EV communication protocols. The first one is the in-vehicle communication networks. So in-vehicle communication network is the network which is created internal to a vehicle. Nowadays, all the vehicles are equipped with the electronic system. All the sensors, all the actuators, whichever is inside a vehicle, is run by the electronic system, and which will sense the data and transfer the data by the electronic system, sensors, or whatever it may be, and it will transfer to a common system called electronic control unit inside the vehicle. So this is controlled by the IVN, that is in-vehicle communication network. So this protocol selection, there are multiple protocols which is used inside the in-vehicle network. So this protocol selection depends on the data rate and the determinism and the fault tolerance and the cost of using this protocol technique. And also mainly we will be using this protocol based on the criticality of the situation, criticality of the sensors, criticality of the data which we need to transfer from one sensor to the electronic system or some other control unit. The first one in the in-vehicle communication network is CAN. This is the CAN bus. It is the common controller area network, which is the common bus which is used in the vehicles. So the CAN is nothing but it is a in-vehicle communication protocol with reduced complex wiring. So it has only two-wire system. It is a message-based system. It will send the data and it will receive the data. It is only a two-wire system, so it will not be complex to implement, and it will be of low speed also. So for normal applications, this CAN system can be used. There are multiple varieties of CAN, that is CAN high and CAN low. Especially this CAN will follow the standard of ISO 11891 for the data link layer and ISO 11882 for the physical layer. In the protocols, in the normal protocols, everywhere there will be a data link layer and the physical layer. Physical layer will be the high-speed interface which will be talking to the external world, and the data link layer will be the layer which is processing the data and sending to the physical layer. So there are multiple variants of CAN. One is CAN FD, that is flexible data rate for longer payloads and faster speeds. So longer payloads, if you want to send a bigger data from one peripheral to other peripheral, and for if you want to get faster data, if you want to get it in the speed, high speed, then you can use flexible data rate. And if you want to have greater performance, then you can use CAN XL. And where is it adapted? There is a classical CAN which was used before, so that is there still. Along with that, there is a CAN FD, that is flexible data rate, which is adapted for a 0.1% in the industry. And the CAN XL, it is not yet deployed inside the vehicles. So the main applications of the CAN is for the engine management, braking system, and also for the general ECU. ECU is nothing but the electronic control unit. So in-vehicle communication, this is the diagrammatic representation of a in-vehicle communication. So this is internal to the system. The CAN protocols are there will be multiple sensors inside the system, inside the vehicle. So these communications will be happen through the CAN. There is an electronic control unit 1, control unit 2, it will be capturing the data and sending to the data. But if it is an external well, we have other protocols which is communicating from the external well. So this satellite communication will also happen through other protocol. But from that sensor, this data will be processed through the CAN to the internal unit. The other protocol is in-vehicle communication networks. In that, the other protocol is LIN and FlexRay. LIN is nothing but local interconnect network. This local interconnect network can go up to a speed of 20 kilobits per second. And it is a serial protocol. It is again a serial protocol. Since it is a serial protocol, the wiring is less. It doesn't have multiple, it don't want to have multiple wires, so that the complexity of installing this is very less. And also it is used in the applications like interior lighting and window or mirror controls, door locks, seat adjustments. And also the advantage is simplified wiring. The cost of using this LIN, so everyone has to get a patent or they has to spend some amount to get these protocols from the vendor. So the cost of this protocols will be less, and it also mainly it is low power consumption. The power is also one of the main aspect in implementing these electronic equipments and electronic protocols. So it will have low power consumption. It is a serial bus and it will have only one signal, and it has a built-in error handling technique also. And some of the other applications are of the LIN are the steering wheel control, that is for the cruise control, wiper, climatic control, radio. And also in the comfort point of view, these LIN protocols are used in sensors for temperature, sunroof, light, humidity, and also in the powertrain sensors for position, speed, and pressure monitoring. These kind of applications also, these LIN protocols are used. And also in the small motors and cooling fan motors and control panels for the AC and for side mirrors and windows, seat control, locks, position motors, pressure sensors, window wipers, rain sensors, headlights, airflows. In all these applications, these LIN protocols are used in the vehicles. The next one is the FlexRay. FlexRay is little bit advanced than the LIN protocol. It can run up to 10 megabits per second. So it is bit high speed to the LIN protocol. And these are used in the fault tolerance, and it has since it has increased bandwidth. So these are used in the fault tolerant applications. These FlexRay protocols are used, and these are mainly used in the braking system and the steering, ADAS, and the airbag and control. And even if you take ADAS also use multiple kind of protocols, depends on the functionality and depends on the data it is receiving. So ADAS can use FlexRay protocol for getting the status, and other protocols for some other applications also. The other one is the automotive Ethernet and MOST. The automotive Ethernet is actually a high-speed protocol. So it can go up to 10 Mbps to 100 Mbps speed. So if you want to transfer data at a high speed, then you need to go for an Ethernet, automotive Ethernet. So the main applications of the automotive Ethernet is in the ADAS and the infotainment system, mainly on the high resolution cameras and all. These need high speed data, and they don't want to cameras and all need data very fastly, so that it can process the data, process the images quickly. So in that conditions, this Ethernet, automotive Ethernet has been used. So these are used in the application places where higher data transfer rates than CAN. And challenges are, these are susceptible to RF noise and latency limitations also there in the Ethernet compared to other protocols. And synchronization issues will also happen in the Ethernet if both the ends are not properly connected. And the next one is the multimedia oriented system transport. So in this, it is mainly specialized for the vehicle multimedia networks. It transfers high quality audio and video and data. It is also used for the specific applications when like Ethernet for the infotainment system. There are various speeds. So based on that, we have MOST 25, MOST 50, MOST 150. So these are also the application. This protocol is also used on the video and data processing if you want a very high speed and high definition transfer data. The next one is the external communication protocols for the EV vehicles mainly. So whatever the protocols, whichever we have discussed till now, is the protocols which will be communicating within a vehicle. So inside the vehicle, these protocols will be talking to each other, electronic control unit and the other devices. But there are also communications happening external to the vehicles. So these are the protocols which are used to communicate external to the vehicles. So the main one is the EVSE. So this is the electric vehicle supply equipment which will be used for the charging the communication system, charging the system. So this is mainly used for charging the equipment from the base station to the battery. So if you in this applications also, there are protocols used which we call it as EVSA. And the other protocol is vehicle to everything, that is V2X and telematics. These are the protocols which is used to interact or communicate with the external world like GPS and some other LIDAR and some other external monitoring systems and all. This V2X protocol is used. So this is one of the diagrammatic representation of the V2X and telematics. So here where the vehicle is communicating with the pedestrian to the external vehicle to network, vehicle to infrastructure, something like that, traffic system, and vehicle to vehicle communication. If what is the distance the other vehicle is coming, what is the distance the other pedestrian is coming. So this kind of information can be gathered through the VTX and telematics protocol. In these applications, the V2X and telematic application protocols are used. So there are different variants of V2X protocol. One is V2V, V2I, V2N, V2P, V2G communications. So these are all mainly aimed for the road safety of the people, and also for autonomous driving, and also for the traffic congestion and all. This V2X protocol is used, and also for wireless connectivity also, cellular, Wi-Fi, Bluetooth and all. This uses the V2X protocol to communicate with the external world, and also the telematics control unit. So this will mainly used in communicating with the vehicle to vehicle and external network. And also this protocol is also used to communicate with the GPS system, antenna system, and also some security modules and all are uses this telematics control unit, TCU, telematics protocol. So summary about the automotive communication protocol. So there are, as I discussed, there is a CAN, LIN, FlexRay, automotive Ethernet. Many protocols are there. So the speed of the CAN is 1 Mbps, and it can go up to 5 to 8 Mbps. But LIN is only up to 20 kbps. So beyond 10 Mbps, FlexRay can go up to 10 Mbps speed, and automotive Ethernet can go to 100 Mbps to 10 Mbps to it can go up to Gbps is the Ethernet speed. So based on the speed and based on the need of our applications, we need to select these protocols and we need to use these protocols. So, and also these protocols have other advantages also. This CAN protocol is a multi-master bus. A single peripheral can be used by a multiple masters. So that is one of the advantage of the CAN. So any master can access a particular peripheral. So these are the advantages of the CAN. And the cost of the CAN is medium, and it is also it also has additional features like CRC, error handling techniques. Mainly it is used in the transmission, engine, ABS, airbags, and this kind of applications. These CAN protocols are used. And LIN is a lower speed protocol. It is mainly used in the mirrors, seat adjustment, climatic controls and all. And FlexRay protocol, it is a little bit highly costly, and it is used in the applications like steering and braking applications and stability control, and this kind of applications this FlexRay protocol is used. And Ethernet applications, Ethernet protocol is mainly used in the applications like lidar, radar and infotainment system, and this kind of applications this Ethernet protocol can be used. These are all about the protocols what we have in the electric vehicles. And then let's discuss something about the cyber security vulnerabilities and attack vectors in EV. So before that, if you have any questions, you can ask me, or else I can continue. Hello. Hello.
Sir,
Yeah. If you have any questions, or shall I continue?
yeah, you can continue.
Okay. Screen is visible, right?
Yes, sir. Yes, sir. Visible.
Okay. So the cyber security, mainly the security comes when we are sending a very confidential data between two different devices. But here also the security is important because the protocols can misbehave. Protocols can misbehave based on the data or information which it is receiving. For example, if the braking system is getting a wrong information from some other device, or someone has hacked the braking system, then the braking system will not work properly, so that it can create accidents or some other drastic issues in the vehicle. So this security is also very important, since we are sending the data from one device to other device. No one has to hack, or the data should not loss in between. The data should not corrupted in between. So these things has to be taken care while transferring data from one device to the other device. So the problem with this, since the complexity and the connectivity is increasing, the functionality, the functionality can misbehave, and also there can be chances of vulnerabilities. To avoid this, the cyber security is very much required, and this has to be included in all the protocols. So the general vulnerabilities of automotive network is lack of inherent security in legacy protocols. The existing legacy protocols, there is this uh, security is not, these issues are not expected, so people didn't include the security challenges in the protocols like CAN, LIN, FlexRay. So these protocols are designed without primary cyber security concerns. So the problem is no encryption or authentication is implemented in the CANs are broadcast communication protocols with lacks in sender identity verification. Can send multiple the same data to a multiple devices. Because of that, anyone can receive the data which is coming from the CAN, which doesn't have any identity to which sender, who is my receiver, to whom, to which particular peripheral I am sending this data. So the CAN master will not be aware of that. It will just broadcast the data. It will go to all the peripherals, so anyone can receive the data. So if it is some confidential data, if it is the data which is very sensitive, then that will create an issue to the system or to the external world. Anyone can hack and create issues in the vehicles. So in that case, this cyber security is very much important. And expanded attack surface, like growing connectivity. Because of the connectivity issues are there, many connectivity protocols we are using like Wi-Fi, Bluetooth, and cellular. This introduces remote attack vectors. So because anyone can access and hack from the remotely also because of this. And shift to remote exploitation. Remote attacks constitute 95% of automotive cyber incidents in 2023. So this is one of the representation. So there is a common electronic unit, but multiple radio devices are sending data to an internal control unit. So the internal control unit, if is not aware of the cyber vulnerabilities and cyber security is not implemented in the internal unit, so it will receive all the data and it will process any of the data to any kind of issues in the vehicle system. So CAN bus attacks. So this problem is common to all the protocols whichever is existing in the currently. So whichever this cyber security has to be taken care, or it has to be taken seriously in the protocol designs, and so that the issues can be we will not have these issues in the future. So one is the high vulnerability due to lack of inherent security features. So the CAN doesn't have the security features. So this attack methods in the CAN can be frame attacks using a CAN controllers to send valid but malicious frames. So wrong data can send through a CAN controller, since the receiver will receive the data from any CAN controller which is sending the data to the device. And protocol attacks, direct control of CAN signal lines for timed pulses. So that you can directly send the CAN signals to the peripherals. And denial of services, high priority messages can be if there is multiple messages are sending through the CAN device, CAN protocol, we can send a high priority message so that the peripheral will receive the high priority message and it will process it, and it will lead to some issues. And also compromised ECU, electronic control units will get, if you are disabling some braking system or steering through the ECU units through the CAN networks. And data injection, incorrect data can be sent through the CAN network, and capturing and replying some unwanted messages or unlocking the doors. This kind of issues can be hacked, or this kind of issues, this CAN protocol is susceptible to this kind of issues. So yeah, as I mentioned, two control units are there, two electronic units are there, but the same data is sent to the two control units. So the device doesn't know which data has to be processed. It will randomly pick some data and process it, and it will lead to some other issues. And the other one is the LIN and FlexRay attacks. So here also you will have a single master. It will send the data. It will broadcast the data. It can go to the battery sensor, and also it can go to the airflow sensor. So anyone can process the data. So whether for which sensor it is intended, receiving device doesn't know. So it will take the data. As soon as it saw some data it is coming, it will take the data and process it and do the processing and give the output, and it can lead to some other issues. So the problem in the LIN and FlexRay attacks are response collision, the data link layer vulnerabilities, and header collision, manipulating the header fields to compromise arbitration. So the LIN has the header fields. So this header fields can get manipulated because of this unwanted data which is coming internally. And injection of attack, someone can purposefully send some malicious data to the through the LIN, and error handling exploited, and intentionally stopping communication and injecting false responses. Because the cybersecurity features are not included in the LIN and FlexRay protocols, these kind of issues can be happened. And this is the FlexRay. This is also similar to the LIN. So it will also have the same issues whichever we see in the LIN also. So anyone can hack the data, anyone can send any kind of issues or malicious packets to the protocol or to the network, and so that the receiving end can receive some unwanted data and it can get corrupted inside the system. And this is one of the problems in the automatic Ethernet attacks. So Ethernet, even though it is a high-speed data, and even though it is traveling through the high-speed packed wires, it can also it can also get affected by the noises from the external world or some normal IT networks or any other of DOS kind of things also can happen in the automatic Ethernet system also. And V2X and telematics attacks. So V2X and telematics are mainly used for the external world communication. So if you are getting some wrong data from the external world, if you are getting some collision kind of wrong data from the external world, some other external vehicle is hacking the control path and sending some other data, wrong data to the system, so that the system will get stopped, or sometimes the system will go faster, the vehicle will go faster, since thinking that there is no data, no people surrounded, so or no people are surrounded, no pedestrian are surrounded. This kind of attacks can happen in the V2X and telematics protocol, so which will create problem in the vehicle system, and it can lead to the accidents also. This is also same as the telematic V2X and telematics. So the external world can hack the data and send wrong data to the internal system, and the internal system will process the wrong data, since there is no proper security involved in the V2X and telematics protocols. So there are few of the research problems and opportunities in this. So one is mainly, since the protocol, already we have many protocols evolved in the EV and electronic system, but the security point of view, these things are not there. So this security can be mainly implemented through the AI model, since the AI is one of the emerging field nowadays. Many AI techniques or AI models can be implemented to find the robustness and develop accuracy between the data transferring from one system to the other system, and also optimizing the cryptography, the crypto options in the design, in the protocols, and in the supply chain point of view, frameworks are tools for continuous security verification. For the continuous monitoring system kind of things can be implemented in the protocol, so that the data whichever is transmitting between two different protocols will be stable, and the other device can make sure that the data whichever is received is proper. And the data between the sensors, there will be multiple sensors used in the EV vehicles, so the data integrity between the sensor, whether the data whichever is coming from one sensor is correct, and that is the actual data which has to be processed by the control unit. So this kind of differentiation can be made using the AI driven system. And also there can be research automated workflows for identifying, patching, and responding to the issues or malicious packets which is coming from the external world. So these are some of the research problems which is related to the security and the protocol of the EV vehicles. So that's questions or anything, I can answer you.
So now it's the time for participants to ask questions. If there is any question, you can ask now. You can also message in the chat box.
Participants are kindly requested to post their questions in chat box or could unmute one by one. Any questions? So, okay, it seems like all the concepts were explained so clearly that there are no questions at the moment. So,
Okay.
thank you once again, sir, for such a comprehensive session. So, as a token of our gratitude, we would like to present a virtual memento to Engineer Aicte-Atal for gracing us with his expertise and valuable time today.
Okay.
Sir, is there anything to present? Or?
Sorry, to me?
Yeah, sir.
No, I don't have anything.
Oh, okay. So can you?
Yeah.
Okay, thank you, sir, for joining with us for this session. Okay, thank you for your informative session and joining with this joining with us for this time because of your in the midst of all the busy schedule, you come here and come here in the online mode and find time to do this online session. So thank you on behalf of Christ Engineering College. We thank you.
Thank you very much.
So our next session will start at 7:30 p.m. So you can now now you can have a break and rejoin. So good evening, one and all. Welcome back to the fourth day sessions on AICTE training and learning sponsored online FTP program on emerging trends in electric vehicle ecosystem, power electronics, AI, and sustainability. Now we have our second session, that is BLDC session on BLDC motor for electric vehicle. The session is going to be handled by engineer R. Akhil Raj of ISAB India Limited. I request Ms. Anne Rose, student volunteer, IEEE, student branch, Christ College of Engineering, to officially introduce the resource person and officially welcome him to the session. Over to you, Anne.
Thank you, ma'am. We are delighted to welcome Engineer R. Akhil Raj, who is presently associated with ISAB India Limited and has recently completed his research as a research scholar in electrical and electronics engineering at the National Institution of Technology, Calicut. Engineer Akhil Raj is an accomplished professional with a strong foundation in power electronics, hardware development, and electrical drives. He holds an M.Tech in electrical drives from Maulana Azad National Institute of Technology, Bhopal, and a B.Tech in electrical and electronics engineering from the College of Engineering, Trivandrum. His doctoral research at NIT Calicut 2019-2023 focused on advanced application in power electronics and control, showcasing his commitment to innovation and R&D. Professionally, has a rich background spanning both industry and academia. He served as an assistant professor at Providence College of Engineering, Kerala, where he has mentored and guided aspiring engineering for over 3 years. His journey reflects as a blend of practical engineering expertise and academic excellence. With his deep knowledge in TM320 processor, power electronics, and hardware development, Engineer Akhil Raj continues to contribute meaningful to both industry application and research advancement. Let's extend a very warm welcome to Engineer R. Akhil Raj.
Thank you, Anne. Thank you for the introduction. And thank you, Christ College, for providing me this opportunity. Am I audible?
Yes, sir. Yes, sir. You are audible.
Yeah, great. Thank you so much. I will share my slide. Just let me know
Okay,
whether
sir.
it is visible or not.
Okay, sir.
Is it visible?
Yeah, yes, sir. Yes, sir. It's visible.
Yeah, great. So thank you so much. Once again, thank you so much for the introduction. So I will be presenting the work which I have carried out during my PhD research work, which was basically for reducing the commutation torque ripple in BLDC motor. And this motor and this research we have conducted for mainly for using this BLDC motor for three-wheeler application. So what was the research of the motto of the research, and how did we arrive that how this commutation ripple can be reduced, and what is commutation ripple, how we can differentiate a BLDC motor from a PMSM motor. So I will take you through step by step. If there is any doubt regarding anything, just let me know. And before starting, I will give you a brief introduction about my company. So ISAB is a very old company which has been there for almost 120 years. And we manufacture everything, whatever is required for welding, from welding material to welding machines. So I'll show some few slides regarding our company. So the first logo of our company was introduced in 1973, and and then there was advancement since there from till now. So ESAB has different kinds of welding applications like friction welding application machines. We have high-speed submerged arc welding machines. We have hybrid laser potential machines. And all these are included with the next generation technologies. And so much is there. So I will not be able to share all the information here, since the motto of this, the FTP is different. So for a brief introduction, ESAB has their own manufacturing units for materials which are used for welding application, like the fluxes, the alloys which are used for welding, the low alloyed steels we have, mild alloyed steels we have, spool type steels, spool type welding materials. Then we have gas equipments type of welding equipments, and these welding the ESAB manufactures everything which is required for these equipments, like torches, regulators, cutting tips, everything. Then we have arc equipments which are which are used for the basic welding application, like MIG and MAG, and TIG application. MIG is basically used for applications where inert gases are used to provide isolation from the atmosphere during the weld process. So then we have automated welding machines which are used by the industries for without any human efforts, but just providing the instructions. The complete weld can be done with this automated machine. Then we have manual machines with plasma. So with the help of plasma, a precise cutting capabilities can be obtained by up to 1/8 of inch to 4 inches. So this is just a brief about my company. So I will jump on to the main content of this FTP. So this is the outline. The first I will be providing basic introduction. Then I will be showing how we can differentiate between the PMSM motors and BLDC motors. Then I will be providing the brief introduction about the BLDC motor. Then I'll discuss about the two-phase conduction of BLDC motor, and how then the topologies which we have selected for reducing the ripples in the BLDC motor. Then finally the results which we have acquired during the after the implementation of this topologies. So, in order to differentiate between a BLDC motor and PMSM motor, the basic difference between a BLDC motor and the PMSM motor is the back EMF. So, in order to find out the, in order to differentiate between these two machines, we have to generate the back EMF. We have to measure the back EMF across the stator of the machine. So here you can see on the left side, I have shown a scope result in which you can see three square waveforms, which corresponds to the Hall signals of the of the machine. And at the top of this, you can see, is my slide visible?
Yes, sir, it's visible.
Yeah, I show the laser point. Yeah. So here you can see, here you can see a sinusoidal waveform. This is the back EMF received from the stator of the machine, and on the right side, which corresponds to the back EMF of the BLDC motor. Now the difference between these two waveforms, you can observe, this is a perfectly sinusoidal waveform, but the back EMF corresponds to a BLDC motor has a flat topped back EMF waveform, which is called as the trapezoidal back EMF waveform. Now, operating a motor with a trapezoidal back EMF, what is the advantage? So in order to understand that, if we conduct a test with respect to the power output with respect to a sinusoidal waveform and have a trapezoidal back EMF, and taking a square waveform current. So here there are two types of back EMF as I've discussed. So a trapezoidal back EMF and a sinusoidal back EMF, and both are excited with a square wave current. Now in these two cases, you can see here the if we multiply this sinusoidal current with this square wave current, it will ideally result in a power of a power which is lesser than the trapezoidal back EMF. So from the waveform itself, you can observe that the current is cut off when the back EMF is constant. So during the change in the back EMF, there is no current. But at the same time, there will be current in other phases. But for the phase which is shown, the current is only conducting during the flat top phase. So if we ideally observe, during this ideal condition, if we multiply this current and back EMF, the output torque should be constant. But in the case of a sinusoidal waveform with a square wave excitation, you can see there is variation in the output torque. So if I calculate the power in this case, it will for the trapezoidal back EMF with a square wave excitation, it will provide at output average power of 3.15. But in the case of a sinusoidal waveform excitation, back EMF excitation, the average power will come around 3. So here I have assumed the values as a normalized value with RMS value of 1. So based on that, I have done the calculation. So you can see with trapezoidal back EMF, there is an increase of 15% power delivered at the output side. So this is the advantage of using a BLDC motor. Now, even though having a 15% of advantage, BLDC motor suffers with lots of disadvantages, lots of issues. So, and in order to take the advantage of this particular wave shape and the current excitation, the method which is used is called the 6-step square wave current excitation, or in other words, it is also called as two-phase excitation. So I will discuss about this. So before that, the another differentiation in BLDC motors are with respect to the rotors. So when it comes to rotor can be manufactured in two ways. One is called the SPM rotors and another is called the IPM rotors. SPM rotors basically corresponds to surface permanent magnet rotors, and the another IPM rotor corresponds to internal permanent magnet rotors. Now, for obtaining a better trapezoidal waveform, usually IPM rotors are considered, and IPM rotor also has some advantage like robust construction, which helps them operating at higher speeds. So over and above this, the IPM configuration has the better advantage of giving better wave shapes with respect to the SPM rotor. So on the figure on the left side shows the basic configuration of a BLDC motor. So it has a 3-phase inverter, which is connected to the stator winding of the BLDC motor. Now Hall sensors are connected in the BLDC motor stator, and which is which gives the feedback to the commutation logic generator, which controls the inverter, and hence the switches are controlled, and based on that the motor produces the output torque. Now, to take the advantage of the square wave excitation with trapezoidal back EMF, the best way is to switch with 120-degree switching, so which is also known as two-phase conduction. So two-phase conduction basically corresponds to the idea that at any given point of time, only two-phase will be conducting. So here you can see the first three waveforms basically shows the output of the Hall sensors. So each Hall sensor will be conducting for a 180-degree. And the difference between two Hall sensors, the phase difference between two Hall sensors will be 120-degree. So for a given 120-degree, a given two phases will be conducting. And so in corresponding to that, for the 120-degree, the back EMF will be flat top, corresponding to that particular phase. So here, yeah, three phases are shown and corresponding currents are shown. So at in any of the sectors, here you can see the phase A is conducting and correspondingly the lower side of phase B is conducting. So in the next sector, similarly the positive side of the phase A is conducting and the negative side of phase C is conducting. So when the motor is rotating from sector 1 to sector 2, the phase A is remaining in conduction, but there is commutation. That means current is changing from lower switch of phase B to lower switch of phase C. Similarly, going ahead, there will be one phase which will be always in conduction, and the other phase will be keep on changing. Now, so if we analyze this waveforms, so at any instant you can see any instant if I multiply the back EMF and current, you can see if the total the total torque will be equal to the multiplication of the conducting two phases, which will give the output torque. So ideally we should get a constant torque, but still due to the presence of some non-idealities, the machine is not capable of providing ideally constant torque. So these are some of the major reasons due to which the machine fails to provide the constant output torque. So issues like harmonics in the back EMF, the back EMF may not be a proper flat top trapezoidal waveform. The issues like cogging torque, the issues like the practical constraint of the train, like practical constraints of the drive, and ripples in the ripples which are generated by the rectifier will also cause the issue in the producing the proper torque waveform. The major issues which we have tried to address was the stator inductance and the phase commutation. So phase commutation, as I have discussed, is the change of current from one of the phases to the other phase. The another issue is related to the presence of stator inductance. Even though BLDC motors are having low inductance, but this presence of inductance does not allow sudden change in current. So this expected square wave current cannot be achieved due to the presence of this stator inductance. But how this is affecting the the commutation between two phases, I will be showing in the upcoming slides. So, in order to break down this issue, the one complete cycle of a BLDC motor can be divided into two periods, which is called one is called the conduction period, the another period is called the commutation period. So here, the period which is marked with the red line is basically the conduction period. Here you can see the phase A and phase C are conducting. The positive switch of the phase A is conducting. At the same time, the negative switch of phase C is conducting. So this period is called basically the conduction period. And the instant at which the commutation happens is shown with blue arrows. So the phase A is going out of conduction and phase B is coming into the conduction. So so basically the positive current is commutating from the positive from phase A to phase B, but the phase C is still remaining in conduction. Now, during this instant, we are expecting, if we are expecting ideal behavior, the current should ideally shut down at the same instant when the back EMF starts reducing. But this does not happen because of the reason what we have discussed is the stator inductance. So this ideal behavior of the current wave shape deviates, and we obtain something like what I have shown here on the left side. The current wave shape deviates from the ideal behavior, and the output current across the line looks something like this. So this is called, basically it is called as a crown wave shape current, which is peaky in nature. So this is the instant at which commutation is happening. So the current starts slowly degrading, and at the same time, the next phase current starts slowly increasing, which results in a crown wave shape. And the resultant output torque, which should be ideally a constant waveform, looks like something like this. Now, in order to address this issue, there are different methods are employed in the used by different. So what we have done, we'll discuss in the upcoming slides. So in order to understand how this issue is arising and how this issue can be resolved, we have mathematically we have break down the entire operation of the conduction period and the commutation period. So this the conventional structure is shown on the left side, and if we write down the KVL equation, which is shown in equation 1 in matrix form. So each phase we have taken the neutral point voltage. So each phase voltage equation will correspond to the resistance, the back EMF, and the drop across the inductor. So the resistance into current is a drop across the resistance, and then next corresponds to the drop across the inductor and the back EMF and the neutral point voltage. So the torque for a given BLDC motor is the torque should be equal to the multiple product of back EMF and current. So since we are taking a two-phase conduction, so we are assuming that only two phases are conducting and at any point of time. So in one of the phases, the current will be 0. And if it is an ideal case, the current in the two phases should be equal. This will result in a total output torque of 2EI by omega L. But due to presence of this non-ideality, I will be share this torque is lesser than this. So, in order to understand how the motor is appearing during the two-phase conduction, so this is the conduction period during which the phase A and phase C are conducting. So here I've shown the equivalent diagram in which the phase A and phase C are conducting. And during the commutation period, you can see three phases are conducting. Phase A is going out of conduction, phase B is coming into conduction, and phase C is in conducting phase. So this is the equivalent diagram in which the phase B is coming into conduction, phase A in which ideally the upper switch should be conducting, but due to the presence of inductor which stores some energy and which does not allow the sudden jump of current from the conduction phase to this conduction. So this stored energy is basically freewheeled through the freewheeling diode, which is present at the lower leg. So the current is basically still present in the phase A. So this creates ripple into the system. Now, ideally, when we are using a two-phase conduction, still during the commutation instant, all the three phases starts conducting. This creates ripples in the system. So if we mathematically view this, we can analyze how the system, what amount of ripples are present in the system and how this ripples can be reduced. So on the left side of the figure, you can see the phase A is going out of commutation and phase B is coming into conduction phase. So ideally, we were expecting a sudden shutdown, but due to the presence of inductance, it slowly decreases, and the phase B slowly increases. So at the commutation during this commutation instant, if I write the KVL equation, which is shown in equation number 3, so since phase A is connected to the ground, the voltage across this particular phase will be 0, and the current flow, the KVL equation can be written as shown, as this is shown. And phase B is coming into conduction, which is connected to the supply voltage, which will correspond to this equation. And phase C is again with respect to the ground. We can write with respect to the neutral point. This will be the equation. Now, since this is basically BLDC motors have a star connected winding, so the sum of total current will be 0 at all times. So if I replace this condition in this, the neutral point voltage can be found out. So this neutral point voltage, if I replace into equation number 3, the rate of change of current in all the 3 phases can be found out as shown in equation number 5. Now, here, since phase B is coming into conduction and phase C is already in the conduction, so we can assume that the phase B back EMF will be equal to E, and phase C back EMF is equal to minus E, which is that's how this equation is obtained. And EA corresponds, since at this instant the EA starts decreasing, the back EMF in phase A starts decreasing, so that's why it is kept as a variable. So if we further simplify the equation of the phases, the 2 phases which are going out of conduction and 1 phase which is coming into conduction, the rise time and fall time corresponding to the phase which is coming into conduction and going out of conduction can be found out. So the fall time of which is required for the phase to come out of conduction, and the rise time which is required for the phase to come out of conduction can be found out by solving the previous equation number 5. And similarly, and the torque generated during the phase commutation instant can be written as shown in equation number 7. So we know during this instant the EB will be equal to minus EB and EC will be equal to E, and the electromagnetic torque during the commutation instant can be given like this. So if we assume the phase A back EMF is equal to E, the equation can be simplified like this. So this is the torque equation during the commutation instant. So since the BLDC motors has very low resistance, so if we ignore this, ignore the resistance, the electromagnetic torque during the commutation instant will be sum of this part and VDC minus 4E by 3M. So which is basically called the ripple torque. So here you can see, based on this, we can arrive at 3 situations, which will give the rise time, which will give the difference between the rise time and fall time. So if the applied voltage VDC is greater than 4 times of E, the fall time will be greater than the rise time, which is shown in this figure. And if the VDC is less than 4E, the fall time will be less than the rise time. And if a condition comes where VDC is equal to 4 times of VE, that means the voltage which is applied across the inverter during the commutation instant is equal to the 4 times of back EMF, the rise time and fall time will be equal, and the corresponding, there will not be any ripple in phase C. So here the other 2 conditions which correspond to difference in fall time and rise time, you can see there is some ripples in the phase C. So this is the condition. From this mathematical analysis, it can be understood that this is the condition in which the rise time and fall time, and by making rise time and fall time equal, the commutation ripple in BLDC motor with 2-phase conduction mode can be reduced. So in order to achieve this condition, which is not possible with just an inverter. So the basic approach for reducing this is using a DC-DC converter at the front end of the BLDC motor, which is connected before the inverter as shown in this figure. So this is very conventional topologies which is used, used significantly in many applications, which has a DC-DC converter at the end. Now the function of this DC-DC converter is basically to provide a back EMF which is required at the instant of commutation. Now here you can see 2 switches. So these switches basically operate based on the Hall sequence signals. So the combination of Hall sequence will provide the information when the commutation is going to happen. Based on this switch, SN will be connected across the inverter, and the DC-DC converter is regulated in such a way that it provides the required voltage, which is equivalent to 4 times of back EMF to reduce the torque ripple. So during our research, we have actually proposed a new topology, which consists of a DC-DC converter with an added capacitor. So this advantage of this type of topology is that the required DC voltage to operate the BLDC motor is comparatively less than the conventional topology. So since during the normal conduction of the motor, this capacitor will be coming in addition to this DC bus, I mean the input battery, so which will be aiding for the normal operation. And similarly, when the switch S in is connected, it will be aiding during the commutation instance. So both the function which is required for producing higher input voltage is also acquired with this proposed topology. So the topology which we have implemented for this research work is shown in this figure. This is a basic DC-DC. This is a basic DC-DC converter which is known as hybrid chip. So you can see this basic configuration corresponds to a boost converter which has an inductor in series with the DC supply and a switch connected in parallel to it. So this part is basically correspond to a boost converter. Now the extra additional part is the cross-connected capacitor. Now, due to the addition of this part, the gain of the boost converter is increased by 1 plus T. So, by using the voltage balance principle on the input and output inductor, this voltage equation can be found out. Now, this topology is implemented as shown in this figure. So since the output polarity is opposite with respect to the input polarity, that's why the cross connection is done. So this is how it is connected. Now once we have used a diode, so instead of going for a complicated system, a diode is used. Since whenever the switch SN is turned on, the input voltage will be, the voltage across this point will be higher than this point. So the diode will automatically will go into reverse bias. So active switch is not required. That's why a diode is used here. So this topology was implemented. Now, in order to operate this and what should be the duty to produce the back EMF, the formulas are used as shown in. This is the conventional formula of the back EMF calculation of the BLDC motor. And this is placed in the previous voltage equation to find out the duty required to produce the VDC voltage. So we have simulated this on the MATLAB Simulink platform, which with the motor parameters are shown on the left side, and the DC-DC converter parameters are shown on the right side. So this figure shows the basic output, basic without any converter, without any compensation. This is the phase current and electromagnetic torque. So here you can see that this is the crown-shaped current which I was talking about. So the expected current, the current wave shape jumps from 1 to approximately 1.7 and 1.9, then comes back, and this results in a torque waveform which oscillates from 0.8 to 1.5. So basically, the ripples in the output of the BLDC motor is very high. Now, after implementing this topology, the ideal wave shape, approximate ideal wave shape can be achieved. So the rise time and fall time is reduced to a very significantly reduced. So the total electromagnetic torque ripple has significantly reduced. Here you can see. And the oscillation is between 1.24 to 1.28, where in the previous case, the total oscillation was around 1 Newton meter. Here it has been significantly reduced. So this is the control algorithm we have implemented for this topology. So for controlling the speed, the PWM controller is implemented, which will give the PWM, the required PWM for the inverter switches, and the speed of the machine can be controlled. So this whole operation is based on the Hall sensor feedback. So Hall sensor feedback is taken for the speed estimation and duties to generate the duty of the inverter and for the edge detection. So edge detection is basically the fall time, and the Hall sensors Hall sensor edges are detected, which correspond to the rising edge and falling edge. So whenever there is change in the Hall sequence, it will determine, and the counter will start counting based on the time period, the rise time and fall time. Based on the rise time and fall time period, the counter will be set, and this switch is turned on and turned off based on the rise time and fall time calculation. So once that information is provided, the switch is operated, and based on this, the back EMF is applied across the machine, and the required time is calculated. So if the time is properly calculated, the ripples can be reduced significantly. Now, the PI controller, based on the reference speed, will set the DC-DC converter value, and the machine will be the DC-DC converter will produce the required voltage for reducing the torque ripples. So these are the hardware results which we have obtained for that operation. So here the top waveform basically shows the conventional operation with two-phase conduction, in which the torque ripple you can see. Now this is with the DC-DC converter, in which approximately that torque ripples are reduced significantly at the same time. The current wave shape is close to square waveform. So this is with respect to 1000 RPM. This one is with respect to 2400 RPM, and this is with respect to 1 Newton meter torque. And this is with respect to higher RPM now of 3500 RPM. And the bottom figure you can show is the output of DC-DC converter. So whenever there is a commutation instant, the output of the DC-DC converter goes high, and it remains high for the given commutation instant, which will reduce the torque ripple. So this is the consolidated results of what we were discussing. So for all the three instances, and we have calculated the speed for 3 instances, one for 1000 RPM, 2400 RPM, and 3400 RPM. And this is the uncompensated system. And the figure B shows basically the compensated system with DC-DC converter, and figure C corresponds to the output of DC-DC converter. So this is it.
Okay, thank you. Now the participants can ask questions.
Thank you.
Hi, sir.
Hi.
Sir, I have a doubt. Is
Yeah.
it possible to reduce the torque ripple in BLDC motor by implementing a switching scheme? I mean, in BLDC, torque ripples are reduced mainly due to commutation.
Yes.
Is it possible?
Yes. By switching a scheme also you can reduce. So there are different PWM schemes are available.
Okay.
So if you want to, depends upon your application. So what kind of application you are going for, you can choose whether you have to go with a DC-DC converter, because the DC-DC converter will make the system a little bit more bulkier. So if you and also there are some limitations with the switching scheme. So the reduction in commutation torque can be achieved up to an extent. So let's say we were capable of reducing this torque ripple up to 18%. So with this, the conventional scheme, this torque ripple can go up to 50%. But the scheme which we have proposed, we were capable of reducing it to 18%. So similarly,
Sir,
if you
is
go,
it possible to 18%, or by comparing it with conventional method, is it possible to reduce by 18 as compared from the conventional method?
yes.
Okay, sir.
Conventional
Sir,
scheme, yeah.
by applying a PWM pulses into the switches, it will increase the stresses in the switches, right?
Right.
Yes. So we need to apply the PWM pulses at the time of commutation only. Is it possible?
Yes. So there are schemes. in which PWM means basically during this instant, during the commutation instant, you have to implement a three-phase conduction scheme. So in this three-phase conduction scheme, you have to ensure that the PWM scheme should be in such a way that the outgoing phase time and the incoming phase time is controlled, and they should match with each other. So if you can implement such a PWM scheme, you can reduce the torque.
Sir, is it possible to use the duty ratio for that PWM scheme by using any other paper or any other methods?
No, duty ratio implementation. I mean, duty ratio we apply during the conduction period.
Yes.
So if you want to reduce the commutation ripple, it is not equivalent to duty ratio. Means duty ratio will correspond to your calculation of rise time and fall time.
Fall time, okay. Sir.
Yeah. So how you create the logic? So you can create the duty will not be constant. If you apply a constant duty in the outgoing and incoming phase, it will not result in a reduction in torque ripple. So you have to keep a variable duty. So this variable duty will affect your frequency, and stress on the switches will be there. But the advantage will be that the system will not be bulkier, even though there might be some higher switching losses. But you can compensate that by saying that the system is not becoming bulkier. The another disadvantage is this method. You will have more issues when you are operating at high speed with high switching frequency. So let's say you are going for a high switching frequency with some silicon carbide or GaN devices. You will have more stress on the switch. So obtaining perfect commutation will be becoming more difficult. So with the variable duty, so your duty might be going less than 1% also at some instant. So achieving that can be a little bit difficult.
Okay, sir. Thank you.
Yeah.
Any other questions? Okay, I think we can wind up the session. Thank you, Aicte-Atal sir, for having giving such an informative session for us. Of course, it will be helpful for the sales colleagues among us who are doing the research in the BLDC drive in electric vehicle as well as in other areas also. So, on behalf of the organizing team and the Christ Engineering College, and in the name of Department of EEE, Electrical and Electronics Engineering, we would like to have a memento and certificate for you.
Okay.
With us today. Okay, thank you, sir.
Thank you so much.
On behalf of everyone, here we sincerely thank you, sir, for your time, knowledge, and inspiring presence today.
Now the feedback link will be given to you in the for all the participants, and tomorrow also the session will start at 6 p.m. sharp. All of you please kindly join before 6 p.m. And one more announcement, you can now log into your portal and see if there is any examination. A link is provided in the in your portal. Okay, I will detail the procedure for the examination. There will be a short examination on Saturday from 6:30 to 7:30 p.m. So you will have some questions of 20 questions from all the sessions. Okay, altogether 20 questions from all the sessions. The questions will be will not be that much difficult. So you please go through the PPTs which is shared by the resource persons, and I shared them all in the group also. So today, when you get time, you go through the portal and check whether any link is available in the exam page. On the left side, there are some tabs are there. So please go through it, and in the exam page, please see it whether there is any link. If there is no link, please inform me. Okay, I will share you the procedure in detail. Okay, so thank you for joining today's session. Thank you all the participants who are joining today's session, and thank you the volunteers, IEEE student volunteers for assisting the organizing team. So on behalf of all in the organizing team, I wish you a very happy or good night to all. Thank you.